Hi guys, so today we're going to continue on with exercise 2.3 from the Jacplus textbook, and this is the third video, and the final one for this these examples, and we're still solving trig equations. Look, these are a little bit harder and they involve identities, so we got to be really on the ball with that. So look, the first one, we're looking at sine 2x equals cos 2x, and we have a domain of 0 to 2 pi. Now, like I talked about in the previous videos, I'm going to be solving without changing the domain, and I think people understand this a little bit more clearly when they're first doing trig, so that's why I'm going to do this. Now notice that as we do these, there's probably going to be quite a few solutions. So in some cases it would be better to do a general solution in order to solve these, but we haven't covered that yet. So we're just going to use the way that we've been doing, going around the unit circle. We'll cover general solution in another video. So let's see, sine 2x equals cos 2x. I'm going to divide those by cos 2x. And that's going to give me, well, sine over cos is tan. So remember, tan equals sine over cos. That's really important. So that gives me sine 2x over cos 2x equals cos 2x over cos 2x is 1. And as I said, that's tan 2x equals 1. So like we did in the previous video, the part 2 from this exercise, I said let z equal 2x. And therefore, tan z equals 1. So this makes it quite nice because we can draw our unit circle in relation to z. And we can say, well, here's 1 in the table of exact values. That gives us pi on 4 as the angle for tan. And that's a pretty easy one anyway to remember. Tan 45 is 1, or tan pi on 4 is 1. So we know that tan is positive in the first quadrant because tan is sine over cos, and both sine and cos are positive, so positive divided by positive is positive. And then the next place where we're positive for tan is in the third quadrant because again it's sine over cos, and in this case both sine and cos are negative, so negative divided by negative give us positive. So look, let's now go about labeling these or finding these angles. So we've got z, and then 2x, and then x. So z equals pi on 4. So that's an easy one, pi on 4. And the next one that we can do would be to here. So to get there, again, let's think this is 0. My denominator for my angle is 4. So I'm going to say this is 4 pi on 4. And then I'm going to say this is 8 pi on 4. It just makes it a little easier to count. So if I go here, I go 4 pi on 4 plus pi on 4, that's 5 pi on 4. So now I can say, let's find out what they are. 2x is going to be pi on 4, and therefore x is pi on 8. And that is within our domain of 0 to 2 pi. So I'm going to highlight that so we don't lose it in the working out. So now let's do 2x equals 5 pi on 4. That means x is 5 pi on 8. And again, that is definitely within our domain. So I'm going to highlight that. So it seems, you don't have to highlight it, but, it does make sense to do so because really there's quite a lot of working out in these. So you don't want to lose your examples and then lose a mark for just not including one of the answers that you actually have found. So let's go around again. It seems like we can have some more angles here within the domain. So let's go from 0, 4 pi on 4, 8 pi on 4, 9 pi on 4. So that means z equals 9 pi on 4. 2x is therefore 9 pi on 4, and x is 9 pi on 8, which again is quite well within the domain of 0 to 2 pi. And look, if you're unsure, you can always say, well, this is 0 up to and including 16 pi on 8, because then it's really clear, that we're not up to 16 pi on 8. 16 pi on 8 is 2 pi. So we're up to 9 pi on 8. Let's see if we've got another one there. And I feel like we will. So 4 pi on 4, 8 pi on 4, 12, 13 pi on 4. So z equals 13 pi on 4. 2x is 13 pi on 4. and therefore x is 13 pi on 8, and again that's within the domain. So I'm going to go one more. I feel like that's the end of it, and actually I can see that that's the end of it, but we'll go one more because it is good to just check so that you do get all the solutions. So 4 pi on 4, 8 pi on 4, 12 pi on 4, 16 pi on 4, 17 pi on 4. So already you can see that it's not going to work, but I'll show the working just to be clear. 17 pi on 4, so 2x equals 17 pi on 4, and x equals 17 pi on 8, and that's too big because remember 16 pi on 8 is our limit. Too big. And look, you don't need to write too big there. You don't even need to show the working out for that one, but it's just, you know, for your own good to make sure you haven't left any out. So there's all our solutions for the first one, and the big idea there is that we've got tan is sine over cos. So if you didn't identify that you had to divide by cos on both sides, you wouldn't have been able to do that question. Really an important identity there. Let's move on. So let's see, what have we got here? Solve the following equation. 2 sine squared theta plus 3 sine theta minus 2 equals 0. Okay, so this one is screaming at me that it is a quadratic identity, and indeed it is. So you see these quadratic identities quite regularly throughout Year 12 methods in quite a few different topics. So you've got to really be looking out for them. So I'm going to say let Z is always my pronumeral of choice. You could choose an A or a P or whatever you want. Let Z equal sine theta. And be careful because it's not X. So we want to be careful that we're dealing with theta. And actually, here they've written X, which is a bit silly. It's theta. So that's a mistake there. So if we let Z equal sine theta, therefore 2Z squared plus 3Z minus 2 equals 0. So now we've got a situation where we can solve this using the null factor law. So I'm going to use cross multiplication here. So that's going to be 2z times z, and 2 times 1, and that's going to give me 4z minus z equals 3z, and that is what we want. That's our middle term. So it means that in our brackets we've got 2z plus 1 and z minus 2. So I've done something wrong there, haven't I? Yes, I have. Well, I've forgotten the negative, so we're minusing 1 there. There we go. So let's do that again. So, I just didn't write the negative there. I meant to put it. So we've got 2z minus 1 and z plus 2 equals 0. Okay, that's more like it. So now that we've got that, we will solve for z. And we can see here 2z minus 1 equals 0. So z equals half. And here z plus 2 equals 0. So z equals neg 2. So we've got two solutions for z, and that makes sense if we're dealing with quadratics. Where it doesn't make sense is if we're dealing with our trig, and I'll show you why, our unit circle, because, well, if we have z equals half, that means sine theta equals half. And well, that works. We can solve for that, and we will in a minute. But here, if we say sine theta equals negative 2, well, that doesn't work. And the reason being that if you have a unit circle, the radius of the unit circle is 1. So the domain for sine is always going to be from negative 1 to 1. So you can't have negative 2 because your sine value can never be negative 2. So I can just cross that out and say it's outside the domain. It's outside the domain for sine. So we will leave that one out. We can, however, solve quite nicely for sine theta equals half, and we will do that looking in the table of exact values, which of course you need to memorize. But I've got it here so you can see how we get our values. It means that our basic angle is pi on 6. So let's draw that. So here is our triangle here, and we've got an angle of pi on 6, and that gives us a sine value, which is this height of the triangle of half. So it doesn't look like a pi, I'll just change that. So pi on 6. So now we need to, as usual, go around the angle and solve. So we've got theta equals pi on 6. So that's the one that's just given to us there. And then let's go around in the next place where sine is positive. So like here, sine is positive here. And that means we've got pi on 6 in here. And it means that when we go around the circle, well, this is 6 pi on 6. When we get to there, same denominator, 6 pi on 6 minus pi on 6 is 5 pi on 6. So theta equals 5 pi on 6. Now, the domain we've been given here is from 0 to 2 pi. So I can see that there's not going to be any more, but I'll show you so that you can see why. So if I go, well, here's 0, 6 pi on 6, and then this would be 12 pi on 6. Again, I'm putting the same denominator. It just makes it a little bit easier then. So then 6 pi on 6, 12 pi on 6, 13 pi on 6. So that would tell me that theta equals 13 pi on 6, which, well, that is outside the domain. So my two solutions, and my only two solutions, are these two, pi on 6 and 5 pi on 6. So in that one, the actual finding of the angles was pretty easy. You know, we found those solutions for theta pretty well. But what was a little tricky was noticing that we had to use, null factor law and substitute z for sine theta. So we got a quadratic there that we could cross multiply. I could go one further, so I could, check there, but I don't have to, and I did in this case, and I saw that it was outside the domain. So that is our that's that one. Let's move down to the final example here, and this one again we'll need to use a z. So here we've got cos squared 2 alpha minus 1 equals 0, and this time they have made sure that the angle is correct there. The domain from negative pi to pi, so people get really used to 0 to 2 pi and then don't really look carefully enough sometimes. So I'm going to say again, let z equal cos of 2 alpha. And look, if you're not happy with it looking like this, you could write this as cos 2 alpha squared. And some people benefit from doing that, especially in the beginning, because it's a little tricky sometimes to note that the cos squared x or alpha or whatever it is the same as that. So look, I won't do that, but just it's something to keep in mind if it makes more sense to you. So what this means, if z is cos of 2 alpha, it means we've got, therefore, z squared minus 1 equals 0. And again, you can use any pronominal, you don't have to use z. So look, now I have z minus 1, z plus 1 equals 0. And this is again just, quadratic factorization, like a squared minus b squared would be a minus b, a plus b. So we're using that rule there. And now I can say, well, z equals 1 and z equals neg 1. So we've just solved those, and you must remember that, well, z is nothing to do with it. We're looking at cos of 2 alpha. So therefore cos of 2 alpha equals 1, and cos of 2 alpha, oops, I might draw that a little bit nicely, equals neg 1. So let's draw this. So I'm going to draw a unit circle. And let's think, these are the easy ones, 1 and negative 1, but people really don't like them. People aren't able to do it so well. So let's see, where is cos 1? Cos is 1 over here. Cos is our x value, and it's a unit circle. So this coordinate, if we were on a normal Cartesian plane, it would be 1, 0. Well, it's still 1, 0 because cos is 1 and sine is 0 at that point. And over here, well, this is where we've got neg 1, 0. So these are the points where cos is going to equal 1. And again, I'm looking at 2 alpha here. So I could use another pronominal to say, well, we'll use p this time equal 2 alpha. Therefore, cos of p equals 1. And the same thing here. Let P equal 2 alpha. Therefore, cos of P equals -1. So we're drawing for P. We don't have to worry about changing the domain or anything like that. So the first one is going to be that we're going to go all the way around from 0 to pi. And then this is 2 pi over here. So over to here. So our first solution when -1 is going to be pi. So P equals pi. And I can then go around again to -1. It would be, well, I could go this way or I could go the opposite direction to get to here. And if we look at our domain, it's from -pi to pi. So I'm going to go this way to -pi. So in the negative direction of the unit circle, P equals -pi. So let's see what we get for those. Remembering that P is 2 alpha. And then, well, alpha equals pi on 2. And here, 2 alpha equals -pi. So alpha equals -pi on 2. So both of these solutions are relevant for us. They are both values that we would have within the domain. Right, so now let's go around again and see what, well, let's go on the other side for 1 this time. So I'm going to be here, talking about this one. So at this point, well, our angle would be 0. So I'll say P equals 0. That would mean 2 alpha equals 0, and that means alpha equals 0 as well. So now I'm going to go there again. So again, we want to get to this point here, and I'm going to go in the positive direction. So I'll go all the way around, and I'm going to get to 2 pi. So P equals 2 pi, 2 alpha equals 2 pi, alpha equals pi. And that one gives us the largest value that we can have, because remember our domain is from 0 to, from -pi to pi. So pi is the maximum one we can have there. Let's go in the opposite direction. So this time I'm going to go this way, and I'm going to go -2 pi. So this time I'm going to get P equals -2 pi, and that's going to be 2 alpha equals -2 pi. And then that means alpha equals -pi. So again, that is going to be within the domain. It's the lowest value we can have. So we know we don't need to go any further. So let's see, I'm just going to put all those answers in one spot because they're sort of spread out there so that you can see. So that means alpha equals, let's put them in order, -pi. It equals, so we've included that one, -pi on 2. Included that one, 0, included that one, pi on 2, included that one, and pi. So these would be my solutions here. So in that example, again, you had to notice that we had a quadratic identity, and you had to know that you could use something to sub in. Once you did that, it was pretty straightforward. We could solve in the way we've been doing in all 3 videos. So that completes 2.3.